Okay, thank you, Lynn, for the introduction, and thank you really for the opportunity to participate in this symposium. So a few months ago, John Schiffer actually gave an hour-long director's colloquium on the physics associated with CP1. And I'll briefly use my 25 minutes to tell you about the chemistry that comes out of CP1. And so my talk is CP1, New Chemistry, and the Periodic Table. So I want to start kind of as John did in building up what was going on in the physical sciences at the time that CP1, leading up to CP1. And so he covered the physics quite extensively and elegantly. And so I'll cover the chemistry by just putting up the periodic table of the 1930s. And so the periodic table of the 1930s looks quite a bit like the periodic table now, except for some fairly critical issues with it. And so what you'll notice here in the periodic table of the 1930s is that we're missing some elements here, the transition metal, technetium, the heavy halogen, astatine, francium, the heavy alkali metal. And down here we've got these elements arranged in a fourth transition metal series, and also the lanthanides down here. And so John Schiffer asked me at lunch, because he saw my tie, I'm a chemist, so I have to wear a periodic table tie. He goes, how is this arranged? Because he was disturbed by tungsten sitting over top of nitrogen, I believe. And so we can look at the arrangement of the periodic table, and we can approach this from a variety of different ways. So Mendeleev started looking at arranging the periodic table based on atomic masses, and also based on the chemical behavior of these elements. And so fast forward into the 20th century, or the late 19th century, and so what we end up with at this point in the 1930s is that we've now arranged the periodic table based on the atomic number, the number of protons in a nucleus. The number of protons in a nucleus is also the number of electrons in that atom. So across we go hydrogen 1, helium 2, lithium 3, so on and so forth. But also underlying this are quantum mechanics. So as we go down each one of these periods here, what we're doing is increasing the principal quantum number n by 1. So 1, 2, 3, 4, 5, 6, such that the last row of the periodic table is going to have the principal quantum number 7. If we were to actually make super, super heavy elements, we'd be in principal quantum number 8, but we're not there yet. And so we have proton number, electron number, so electrons are where the chemistry happens. And we also have this quantum mechanic going on here so that we also see with the principal quantum number, we get the orbital quantum number, which gives us s orbitals, p orbitals, d orbitals, and f orbitals. And so in the periodic table of the 1930s, we can, aside from being arranged by the atomic number, or the number of protons, there is this lanthanide series popped up here. And what's interesting about the lanthanide series is that this was predicted long before it was actually chemically separated or identified chemically. And so Henry Moseley, doing X-ray spectroscopy, predicted that there would be no more and no less than 15 F elements of the lanthanide series using X-ray spectroscopy. And the reason that he could do that is that he could jump across this lanthanide series over to thallium, lead, and bismuth and see that there was actually something broken, or there was a break in that trend, that periodic trend. So if we back away from the atomic physics for a moment, and we look at the utility of the periodic table to a chemist, what we see is not only the quantum mechanics, but as we go look down these groups, we actually see periodic effects or trends within the chemistry there. So that if we look here in the alkali metals, we all know that these ionize very easily, so well actually that they'll split water, produce hydrogen, and you can watch the YouTube videos of things blowing up when you dunk potassium, for example, in a bucket of water. Also, we can look across these periods now, and so we can see, and as chemists, we can actually develop periodic trends with reactivities. For instance, scandium is going to be principally trivalent, titanium +4, vanadium +5, chromium likes its +6 oxidation state. And so beyond the quantum mechanics of the periodic table and the elegance there, we can also begin to develop systematics of the chemistry. And so leading up to CP1 and its demonstration at the University of Chicago, this is an extremely interesting time to be a chemist and also a physicist. So at this time, the chemistry and physics are really intertwined. And in fact, you have chemists doing physics and physicists doing chemistry. It's all kind of absurd at the moment. But what we see, in 1939, we identify francium. This would be the last naturally identified element. In Italy, Segre, separated technetium out of some irradiated components. We identified astatine in a nuclear reaction, promethium, the synthetic rare earth element, and now what we're getting into is beyond uranium. Uranium is going to be the last naturally occurring element on the periodic table, and so Seaborg, or actually Macmillan, and then subsequently Seaborg and Berkeley produced these synthetic elements, neptunium and plutonium. And so these are going to be historically critical to the impetus for CP1 and the chemistry that's going to come out of them. So now we've completed that periodic table of the 1930s. We now have neptunium and plutonium, two new synthetic elements. And so what's happening around now is that in 1942, the metallurgical laboratory is going to be assembled in February of 1942 at the University of Chicago. And so the Met Lab is founded rather to develop the pile and the chemistry of the pile. So Glenn Seaborg, who liked to keep a really accurate diary, comments at the time actually that Frank Spedding, who is the director of all chemical research at the metallurgical laboratory, charged the chemist with two things, and I'll just read from his notes here. And so Frank Spedding was most emphatic that we chemists keep clear in our minds that there are two goals and two goals only. One is to isolate element 94 from uranium. So element 94 is plutonium. It is about 1 year old at this time. And the second is to understand all of the pertinent chemistry necessary for the construction and operation of the pile. Develop all of the chemistry necessary for nuclear energy technology. So as a chemist, this is quite the weighty challenge. You're given an element, you have no idea how it reacts, you have no understanding of its chemistry. In fact, it's placed in the wrong portion of the periodic table. It's identified as a transition metal and not the actinide element. But second, I'm told, go into the laboratory and develop all of the chemistry necessary to operate a nuclear reactor. Okay. So out of this, I'll just take a brief aside. So we're standing here in the Advanced Photon Source at Argonne National Laboratory. So in 1946, Argonne is chartered as the first national laboratory, and this mission translates almost directly now to use for peaceful uses of atomic energy. And so at Argonne in 1946, charged with reactor development and all of the chemistry associated with nuclear energy technology. And what's fun for me is that I work in the heavy elements group in the chemistry division, and we can directly trace our roots doing actinide chemistry and the fundamental chemistry of the F elements back to this charge in the metallurgical laboratory and the work of Frank Spedding, Seaborg, and all of the titans of chemistry at that time. So just something to be proud of when you think of coming to work. So all of the pertinent chemistry relevant there. So the deployment of nuclear energy on this industrial scale, or what they saw was going to become the industrial scale after the demonstration of CP1, caused the chemists at the time, or really all of the scientists at the time, that this necessitated the development of new areas of chemistry and chemical research. And so I just highlight here, there's some patents. This is actually these patents at the top here for the separation of plutonium from uranium in efforts to close the nuclear fuel cycle. This is actually the patent for the Purex process developed in the actually out of the metallurgical laboratory that's still state-of-the-art in nuclear fuel reprocessing today, which kind of, I think, unfortunate. We can also look huge advances in the fundamental chemistry of just the elements. This is Seaborg's seminal paper proposing that the f orbitals actually hybridize with the d and participate in the bonding. This is a paper that continues to drive heavy element chemistry and actinide chemistry. And then we look at the advent of fields of radiation biology and then actinide environmental chemistry as we look at trying to figure out how to deal with the problems of waste in nuclear energy. So fast forward to the end of the metallurgical lab and the end of World War II in 1945, and this is what the periodic table looks like now. And so Ed Macmillan and Glenn Seaborg were actually awarded the Nobel Prize in 1951, not for synthesizing plutonium, but for synthesizing transuranium elements, and then Seaborg also for putting together his actinide concept or the actinide hypothesis. And so our periodic table now in 1945 looks a little bit different than the one that I showed you from the 1930s. And what I want to draw your attention to now is that the actinide series here, thorium, protactinium, uranium, neptunium, plutonium, at the end of the metallurgical lab's tenure or operation, we'd also identified americium and curium, elements 95 and 96. And these were moved from this fourth transition metal series, actually now below the lanthanides in the 5F series of actinide elements. And this is going to be critical for a variety of reasons. Whoops. Oh. So what's the significance of this actinide hypothesis? Well, as I told you at the beginning of this talk, Henry Moseley had X-ray spectroscopy to determine that there was actually a 4F series of elements there. Seaborg and co-workers at the Met Lab were originally led to believe, because thorium is principally tetravalent plus 4 oxidation state, that it looked a lot like, and its chemistry does in fact look a lot like zirconium and hafnium. Protactinium plus 5, like niobium and tantalum. Uranium, for the longest time, people thought that it was a homologue of tungsten. And in fact, until recently, had been trying to make metal-metal bonds of uranium, thinking that it should behave like a transition metal, when in fact it's a 5F element. So Seaborg was able to arrange these as a 5F series by doing very careful chemistry and looking at periodic trends across there, both in structure and their reactivity. And what was critical to this in the chemistry was that by the time he got out to americium, he couldn't reproduce the transition metal chemistry that he could for neptunium and plutonium. And so what is this? What are the consequences of this? Well, what causes this actually is a relativistic destabilization of the f orbitals, which I'll get into in a few moments. And what this causes is a participation, as Seaborg actually proposed, of the 5F orbitals along with the 6D orbitals, these quantum mechanical constructs that come out of the periodic table, to participate in the chemical bonding. And this is going to be considerably different from the lanthanides, because those F orbitals in the lanthanides are contracted because of relativistic effects and don't participate in any of the chemistry, such that as we move from lanthanum off to lutetium, which is not here, what we see is universally the plus 3 oxidation state, in contrast to the actinides, plus 4, plus 5, plus 6, plus 5, plus, well, there's all sorts of them here, and then 3 at americium and heavier. So I'll state here in the middle of this talk that Chicago Pile 1, CP1, and the nuclear reactor technology that followed was a critical event in establishing the modern periodic table. And so I'll comment on that. And so if we look now at chemistry in the new periodic table, is that Chicago Pile 1 and subsequent nuclear reactors would actually generate macroscopic quantities of new elements. At the time of the metallurgical laboratory, they had produced fractions of a microgram of plutonium, and they were trying to develop industrial scale separations processes based on the availability of microgram quantities of this material. It's an extremely weighty task to charge a chemist with. But after and subsequent with this new reactor technology, we could produce large amounts of plutonium, americium, curium, berkelium, californium, and even einsteinium. So at Oak Ridge, they're in fact producing californium for industrial processes, and what comes along with this actually are some trace quantities of einsteinium. But what does this actually allow us to do? And so we're not only here, CP1 is now building out the periodic table, pushing the boundaries of the periodic table, but is actually going to allow us, with these new materials in accelerators, to synthesize super heavy elements and study their chemistry. So this is the periodic table as we know it, in 2017. And as I alluded to in the beginning now, we've now populated the entire 5F series out to nobelium and lawrencium, and now we have the entire 7th period of the periodic table populated. And this is quite exciting for reasons I'll get into in the next slide or so. And so here we have element 104, rutherfordium, dubnium, seaborgium, all the way out to now we finally synthesized the heaviest noble gas, oganesson, which Seaborg used to be the only living person, or at the time when he was living, to have an element named after him. Yuri Oganessian is now the second person to have that. We have tennessine here, the heaviest halogen, livermorium, moscovium, fluorovium, nihonium, copernicium, and so on and so forth. And so this is kind of an interesting thing in the periodic table, because as we get heavier and heavier, all of these nice periodic trends that we could expect moving across the periods and down groups start to become muddied. And the reason that they become muddied are relativistic effects and spin-orbit coupling. So relativistic effects are going to scale with Z. So as we add more protons or our nucleus becomes heavier and more electrons, we're actually going to have to make relativistic corrections to things like binding energies, to things like if we were to calculate a Bohr radius, we would have to correct for that. And so what we can see is we go across the periodic table from hydrogen all the way out to oganesson, we can see this quadratic behavior in the relativistic effects. And so if we look from hydrogen out to, say, lead, element 82, we see is about a 25% correction due to relativistic effects in some of the electron binding energies. If we go and we look just at the actinide series out to oganesson, what we see just in the actinide series out to from actinium out to lawrencium is that same 25% correction just in the 5F series. So we have significant contributions now from relativistic effects in the chemistry of these orbitals. And so I can show you that a different way, and what that's going to cause is relativistic effects are going to cause the S orbitals, those spherically symmetric ones, to contract, and it's going to stabilize them in energy, but the D and the F orbitals are going to become destabilized in energy, such that because of relativistic effects, we can no longer use our hydrogen-like atom model, where we would expect the 5F orbitals here to be lower in energy based on the principal quantum number 5, 6, and 7, below the 6D and the 7S. When we turn on nature and those relativistic effects, what we see is a reordering of those orbitals. The 5F and the 6D become destabilized, as we would expect from these contributions of relativistic effects, and those 7S orbitals become contracted and stabilized as well. So this should be concerning to you if you're a chemist, because now what we're doing, because of relativistic effects, is we're reordering the valence orbitals of these atoms. And so what does that mean if we start to reorder the valence orbitals of an atom? What do we start to do? We start to change its chemistry, such that an atom that we might think is a transition metal and might behave like titanium, zirconium, or hafnium might now behave like a main group metal, say, I don't know, sulfur or lead. And so are these in fact going to be that extreme? And the answer is yes. So we can push the bounds of studying this chemistry. These are really fascinating systems. And we can look at the fundamental atomic structure near the end of the periodic table. And so there are experiments probing the atomic structure of these heavy and super heavy atoms, revealing chemical consequences of these relativistic effects and spin orbit coupling. So I show you two examples here, two really elegant experiments, one done at the GSI in Germany and the other one done in Japan, where they looked at the first ionization potential of lawrencium. And so why is this an issue? Well, because of these relativistic effects, we don't actually know what the ground state electron configuration of lawrencium should be. People have calculated it, and we come up with different answers. Lawrencium could actually behave like a 7p main group, or it could have that last valence electron in that 6d orbital. And so measuring this, actually, they found out that, in fact, that it's the proper electron configuration is this 5f14, 7s2, 7p. And that's not what we would expect if you were to ask a freshman undergraduate to go and write the electron configuration for lawrencium. They would get it wrong based on their understanding of quantum mechanics. And so it's these relativistic effects that are driving these deviations from these nice, tidy periodic trends that we as chemists love and that you would expect out of quantum mechanics. So these aren't one-off chemical peculiarities that I'm trying to show you here, but this is in fact pushing the bounds of the periodic table and how we describe chemistry in the world around us. And so the nuclear chemist, or if you like, a low-energy nuclear physicist, they've been out studying the chemistry of these super heavy elements. So here, they recently reported a carbonyl complex of element 106, Seaborgium. So we're now pushing super heavy element chemistry beyond just the atomic structure into the actual reactivity of these molecules, and in this case, near organometallic chemistry of the super heavy elements. We can look at element 108, hassium, which sits right below osmium, and the idea here was that it should behave like a volatile tetroxide. It should behave like a transition metal, like osmium, it's homolog. We can also look at bohrium chemistry. We can look at element 112, and now the big debate is over flerovium, element 114, and its chemistry, whether it behaves like a noble gas or if it behaves like mercury because of relativistic effects. So you've probably heard the word relativistic effects enough, and you're probably bored with it, and you're like, so what? What does it matter to me? Well, if you drive a car that relies on a lead-acid battery, relativistic effects and relativity are how you got to work this morning. There's a paper in PRL that's quite the fascinating read, but they did a calculation for the lead oxide, lead-acid battery, wondering where all this voltage was developed in this chemical reaction. And it turns out that if you strip relativistic effects out of those calculations, what you find is that 80 to 85% of the voltage developed in a lead-acid battery is due to relativity. Thank you, Albert Einstein. In contrast, if we go to tin, which also forms a SNO2, like PbO2, and we try to do the same electrochemical reaction, tin sits right above lead in the periodic table, you can't do it, because the relativistic effects that are present in lead are not present in tin and won't develop that potential for you. So it's just not a peculiarity of radioactive elements. So I'll summarize here by saying that Chicago Pile 1 was a launching point for developing the chemistry of the heavy and heaviest elements. And so the development of nuclear energy technology, and with it innovative fuels and fuel cycles, relies on this chemistry. And so Enrico Fermi gave us the nuclear reactor and gave us these elements. And so we're providing back to him as chemists the chemistry to actually develop this technology for energy and electricity generation through separations, material science, so on and so forth. And so I'll argue that the fundamental chemical and physical properties, or I showed you rather, that these are heavily influenced by relativistic effects, fundamental concepts in chemistry and physics, imparting really kind of unique chemistry to these and causing us to question really how we arrange the periodic table once we get down towards the bottom of it. And so as a fundamental scientist or someone who works in fundamental science, I'll argue that we need to continue to study these, the chemistry of the actinide and transactinide elements, because it's not only critical to understanding nuclear energy technology, but simply for discovery and understanding the natural world around us. So with that, I thank you for your attention, and I think thank you.